In this video, we solve problem 2.6.10 from Nagle's Fundamentals of Differential Equations 7th edition. We're asked to use the method for solving homogeneous polar equations to solve the differential equation, and we're given the equation in this form. And then the problem statement says, ignoring any lost solutions, if any, an implicit solution in the form f of x equals c is blank equals c, where c is an arbitrary constant. Now, if we were not told in advance that this is a homogeneous polar equation, we could look at this and tell that it's a homogeneous polar equation, because if I look at this function, I'm going to call it m. And if I look at this function, I'll call that n of xy. This is a homogeneous function of degree 2. If I replace x with tx and y with ty, I can factor out a t squared from everything here. And similarly, over here, if I replace x with tx and y with ty, I can factor out a t squared from everything here. Now, I'm not going to show you that, but you should confirm that to see that that's true, that these are two homogeneous functions of the same degree. But another way that you can tell that they're homogeneous functions of the same degree is just by looking at individual terms and looking at the degree of each term. This is a degree 2 term, and that's a degree 2 term. So that tells me this is going to be a homogeneous function of degree 2, because we're dealing with a polynomial involving x and y, where all of the powers or all of the terms have the same degree. Now, this is not a polynomial function involving x and y because we have a y in the denominator, but sort of treating that rule loosely, if I add the exponents here, the degree of that term would be 2. Now, technically, this is not a polynomial term, but if I add the exponents here, I would also have something of degree 2. So yeah, the 3 plus the negative 1 is a 2. So that is an indicator that this is a homogeneous function if they didn't already tell us that we should use that method. Okay, so now that we know that we're supposed to use that method, we can start by writing the differential equation in this form of dy dx equals some function of y over x or x over y. Either one would be fine. So we want to get dy dx by itself. So the first thing I would do is I would subtract that term from both sides. So we have xy minus x cubed times y to the negative 1 dy equals negative 1 times this. So that would just change the order here. Y squared minus 4x squared times dx. If I want dy dx on this side, I will divide both sides by dx. If I want a function of y over x on this side, I'll divide both sides by this expression here. So it's just a little bit of algebraic manipulation. These guys reduce, and these guys reduce. And now we have a differential equation in that form. Well, it's nearly in that form. You have dy dx equals y squared minus 4x squared over this expression here. And these are two homogeneous functions of degree 2. It's a quotient of homogeneous functions of the same degree. Now, if you have something that looks like this, where you have homogeneous functions of the same degree in the numerator and denominator, and you'd like to write it as a function of y over x, what I recommend that you do is that you divide by the highest power of x. Well, I was going to say highest power of x in the numerator, but that's not quite right. I would divide by x to the second power in this case. Basically, if this is a homogeneous function of degree 2, and this is a homogeneous function of degree 2, you want to divide by x to that degree power. So if those were homogeneous functions of degree 3, I would want to divide by x cubed. Since these are homogeneous functions of degree 2, I want to divide by x squared. And then watch what happens. We end up with y squared over x squared and 4x squared over x squared. And here we have xy over x squared and negative x cubed And that y to the -1 I'll put in the denominator, but we're also dividing that by x squared. And those reduce, and one of the x's will reduce here, two of the x's will reduce there. And then remember this fact, if you have a to some power over b to that power, you can write that as a single fraction to that power. So this becomes y over x quantity squared minus 4 all over y over x minus x over y. And that's equal to dy dx. So all of these equations are equivalent to each other. Of course, assuming that x is not equal to 0, and because of this, y cannot be 0 either. All right, so this is a y over x to the second power. This is a y over x to the first power. That is a y over x, but it's flipped, so that's y over x to the -1 power. So this is a function of y over x. So let's say, note, x over y is the same as y over x raised to the -1. Maybe we should rewrite that as well. So I'm just taking this piece and I'm replacing it with that piece right there. Okay, so that was the idea. We've written this as a function of y over x. And now we want to rewrite this differential equation entirely in terms of v and x, where v is y over x. And we did a lot of algebra to get down to here. So now we're going to let v equal y over x, then solve for y. So y is v times x. And then you want to compute dy. By the product rule, we'll have derivative of the first times the second plus derivative of the second, which is 1 with respect to x, times the first. Multiplying both sides by x, and then differentiating using the product rule. Derivative of the first in this case is 1 times the second plus derivative of the second times the first. Okay, now with that, we can write everything up here in that differential equation entirely in terms of v and x. So on the left-hand side, this dy dx can be replaced by this expression involving v and x. So you're going to substitute that. And then the right-hand side is just f of v, where I've got a v squared there, a v to the first right there, and a v to the -1 right there. So this becomes v squared minus 4 over v minus v to the -1. Or if you prefer, you can call that 1 over v. So we are replacing y over x with v, and we're replacing dy dx with what that expression is in terms of v, which is dv dx times x plus v. Okay, so now we want to get, we want to separate the variables, because this differential equation will always be separable in terms of v and x. Okay, so the first thing that I would do is isolate this term here by subtracting v from both sides. So we'll have dv dx times x over 1 equals v squared minus 4 over v minus 1 over v minus v. Now, in order to simplify this, I see I've got fractions within a fraction. I would recommend multiplying the numerator and denominator here by v, just to get rid of that fraction within a fraction expression. So multiply that numerator by v and that denominator by v, and that's just multiplying by 1. It doesn't change anything. So we end up with v times the quantity v squared minus 4 over, if you distribute that v times v is v squared. V times negative 1 over v is just going to be a negative 1. Okay. Now here, we need a common denominator, and that denominator is v squared minus 1. So we multiply numerator and denominator by v squared minus 1 so that we can write this as a single fraction. And it actually may be helpful to distribute now. We have a common denominator, so we can keep that the same. And then over here, we'll have v cubed minus 4v if we distribute. And we're going to distribute a negative v here. Negative v times positive v squared is negative v cubed. Negative v times negative 1 is positive v. Okay, and we look for opportunities to simplify. The v cubed and the minus v cubed reduce. And negative 4v plus v is negative 3v. So we have this product equals this, and we're really close to isolating or getting all the v's on one side and all of the x's on the other now. But notice what we have on the left-hand side, and this happens pretty much every time you solve a homogeneous polar problem. You end up with a dv over dx times an x to x over 1. We really need that dx to be in the numerator if it's multiplied by a function of x. So we need a function of x times dx. In order to make that happen, we need to take the reciprocal of this side. That's legal as long as we take the reciprocal of the other side as well. So we're going to flip this and flip that. And then it'll be relatively easy to separate the variables from here. So when we take the reciprocal of each side, we get this on the left, and then this on the right. And again, that works because I just had a single fraction over here and something that I could think of like a single fraction over there. So we could just flip everything. And then in order to get all the v's on this side, we need to multiply both sides by dv. And then the variables have been separated. Now over here, I've got a monomial, a negative 3v in the denominator. So I would recommend taking each of those terms in the numerator and then dividing them by negative 3v. If you want, you could factor out the 1/3 or the negative 1/3. That would be fine. I'm preparing to anti-differentiate now. One of the v's will reduce there. And so if we want to, let's factor out a, let's say a negative 1/3. Negative 1/3 times v is going to give me that negative, or v divided by negative 3. And then over here, negative 1/3 times a negative 1 over v would give me a positive 1 over 3v. If you multiply straight across, you get that. Well, I've got rules for all of these pieces, and of course I have a rule for that piece. So the variables have been separated. And we've simplified. And now we want to anti-differentiate each side with respect to the variable that's on that side. So we have natural log of the absolute value of x plus a constant. I'll just let the constant on the right-hand side absorb the constant from the left-hand side. We have a negative 1/3 here. Here we want to add 1 to the exponent and divide by the new exponent. antiderivative of -1 over v is negative natural log of the absolute value of v plus c. And that is close to being our answer, but it doesn't involve y. Remember, v is just something that we made up so that it was possible to separate the variables and get this far. So the last thing we need to do is maybe simplify, but also back substitute. Remember what v was. V was actually y over x. So if I distribute the -1/3, I have this. And I replace v, with y over x. And remember what we were asked to find. We were asked to find a solution in this form. So we want just a function of x and y equals a constant as the solution to this homogeneous polar equation. So we can just move these terms to the other side. So that's one way of writing the answer. If you prefer to get rid of the fractions, you could multiply everything by 6, and you could get rid of the coefficients of 1/3 and 1/6 out front. You could multiply everything by 6x squared if you wanted to get rid of that x squared in the denominator as well. But you can't get rid of that fraction, well, not really, without using some log properties over there. So I guess I suggest that we would stop here. But there are many ways to write this answer. Using log properties, or multiplying by a constant, or multiplying by 6x squared. We could write this in many different forms, and all of them would be correct.